So thanks a lot to the organizers for letting me have this talk. I'm David. I'm coming from Pisa here nearby, from SNS, and today I will talk to you about optimal compression in the realm of cosmic 21 centimeter signal, and this I'm doing with my supervisor Andre Messinger. Okay. I know that part of you are cosmologists, but part of you are not. So I'm just giving a crash course in 2 minutes of cosmology. So what we are dealing with is like a standard lambda CDM model. So we have dark energy, we have cold dark matter, and we know the general story that we have a big bang out of which the universe was expanding. And then the first structures started to form, first stars, first galaxies, and then we are observing this universe at this very moment. And there are several important events in this evolution. For example, cosmic microwave background is event where the universe was cold enough so that electrons snapped into the protons, and this left like a signal, a snapshot of the universe that we see today. And then in this story, where does the cosmic hydrogen 21 centimeter signal comes into play? Well, the thing is that at the very beginning, so from the very beginning up to today, the hydrogen is the most abundant element in the universe. And basically after recombination, it was 100% hydrogen, 100% neutral, more or less. And due to its hyperfine splitting between electron and proton, it emits 21 centimeter light. And then this means that the intensity of the signal imprints in which state is the hydrogen, in which density it is, what radiation it is influenced by, and then we can observe such, in principle, we can observe such signal from these early stages up to the end of reionization. What happened is that when the first stars were formed, they started ionizing, they started creating ionizing radiation, which then stripped away their electrons. And at some point, there was so much of this ionizing radiation that all of the electrons were stripped away. And then we don't have this signal anymore. So here, just as a simple illustration, I'm showing how then one simulation box of such signal goes. So we have different astrophysical and cosmological effects which are influencing the temperature of this box, and at the end of epoch reionization, the full signal is just gone. If we now take this simulation and if we try to see, okay, what would be observed by the telescope, we know that, like, if we have here, we are as an observer, and as far as we look, more in the past we go, and basically in the simulation box, then we are stacking from earlier times here up to today, like a snapshot, a sky plane snapshots of the universe. And that's what the telescope will then observe. And this is what we call the light cone object. So like a three-dimensional cube or cuboid of our signal. And so, as I said previously, the properties of the first unseen stars and galaxies are encoded in both timings of different epochs of the signal. So when exactly are they appearing, and also in the patterns that you can see here. And what is important is that such signal is highly non-Gaussian. And what we would like to do in our analysis is how to then infer those cosmological and astrophysical properties out of such a signal. And underlying question is how to compress it to do such an analysis. Yeah. All right. So so let's say that at the very beginning, as an initial state of the universe, you have that the power spectrum of the matter is Gaussianly distributed. And so basically, then what I mean by non-Gaussian is that that this doesn't hold then anymore later on, because the evolution of the universe is non-linear. So if you would have a linear evolution, then you would stay in a Gaussian regime, but the processes that you have are highly non-linear. Yeah, exactly. Exactly. Yeah, exactly. Yeah. And so this is basically the same slide as I think Marco had. So what we are doing Bayesian inference. So we are asking ourselves, okay, like we have some initial knowledge about our cosmology and astrophysics, and how do we update this knowledge by including new data, in our case, this 21 centimeter signal. And the main ingredients of such an analysis are prior as a first thing. So for the prior, if we have a physically motivated model, then we understand our parameter space and we know how to write the prior on the space. This is very trivial saying, but it goes like it's an important, for example, in this Bayesian neural network learning. For example, when you have neural network and you consider weights as your parameters, this is not a physically motivated model. You don't understand the parameters and you don't know how to write the prior, right? So it is important in Bayesian analysis to understand your prior well. Evidence, it's something that is mostly ignored, except if we are doing something like a model selection. And likelihood function is then where the data comes into the play. And the question is, what is this likelihood function? And to write it down, very often it is necessary that this data is compressed to some set of summaries, and then we are writing likelihood function in this set of summaries. I will give a few examples later so you will know what I'm talking about. So here's our pipeline. So we are basically starting with cosmological and astrophysical parameters, which are then used to simulate our light cone cube. Then additionally, we have effects of the telescope, because we want to fully forward simulate up to what the telescope will see. And so with the telescope, it's adding its noise. Also, we have some other foreground signals which are contaminating this signal, and at the end we get the final result out of our simulation that we then try to compress into some set of summaries. And then when we actually have the observed data that we unfortunately at the moment still don't have in this sky plane image space, we do the same kind of compression, and then we compare those two summaries with in a likelihood function, which can be either some analytic function or something as a likelihood-free inference that we will talk about. Once we have that, then we can recover posterior knowledge of our parameters. So to summarize, two crucial components are how to do the optimal compression of this data cube and how to then, in this compressed space, write the likelihood function. And these are the two topics that I would like to talk about. So to give a few examples, here is what I mentioned, the CMB, which is a snapshot of very early universe. And so we have a very good theory behind it. We know that it's Gaussianly distributed. And so we know that if we take such a full sky map, that it can be compressed into the power spectrum without loss of any information, because this is what theory gives us. And then once we compress it to the power spectrum, this is everything that we need. We don't need a full sky map. And we can have our cosmological model, and we can do the inference of our cosmological parameters and recover the posterior of them. However, let's imagine that you want to do the same thing in this example of this picture of a duck. And let's say that you want to infer some of its properties. Let's say you want to infer the length of the neck, the size of the feathers, or something else on this duck. And now imagine that you Fourier transform it, you shuffle the phases, and you return back. And what you could get is this picture on the right, right? And so both of those pictures have the same two-dimensional power spectrum, but you will have a very hard job in inferring anything about the duck from here. And this is always happening when you have highly non-Gaussian information, in Gaussian in the sense of the power spectrum, right? All right. However, we are lucky that actually with 21 centimeter signal, it is a bit simpler than a duck. And actually, the power spectrum does encode a lot of information about the signal. But we can then go further because we know this is not the whole story. We can try to encode the bispectrum. We can try to add some morphological spectra or something like that. So here I'm just showing plots of them, but they're just as a sketch. They're not important in detail. The conclusion of all of this analysis is that if we add on power spectra such a non-Gaussian additional information, we are always improving the parameter inference. However, as I mentioned earlier, for this 21 centimeter signal, we don't know theoretically, we don't have like some physical motivation of what such a compression should be, and what compression would give the tightest constraint on our parameters, and therefore the approach that we and many others chosen is let the machines figure that for us. And by machines, we mean neural networks. Once we decided to go with the neural networks, important point is, as we heard also today, how to then design neural network that matches perfectly your data, because like different neural network designs will better or worse encode your information. And I don't think I have to introduce this, but some two very famous architectures are convolutional neural networks, where we are trying to use local correlations in the image, or recurrent neural networks, which are dealing with sequential data and they're encoding better sequential data. So what is about the LightCon then? Here I'm showing just one funny example of how one could think of LightCon. So here we have time going from top to the bottom, and here is our signal. And then here's one video of a cat where it's filmed, and only one particular snapshot at the time is kept of this cat. And this is exactly what the LightCon is. And so we are trying to learn something out of such a data structure. So what we did is that we basically combined those two architectures into one. So in the sky plane, we have normal images, and we know that the CNNs are well constructed to encode local correlations in images. And on top of that, we used recurrent neural network to encode correlations across frequency bins, because in our LightCon cube, we have evolution, some kind of both spatial and time evolution in this redshift or time domain. And we did that on a database of 10,000 simulations. For this, we used semi-numerical 21 centimeter fast code. And then additionally, we contaminated those images with these effects of the telescope and foregrounds. So firstly, we had to remove the mean of the signal. just because it will be detected with a radio telescope, so we will not be able to infer the mean of the signal. Then we are adding the noise of here particular square kilometer array, which will be built in the future, which also smooths out our picture. And finally, we are removing the parts of our data that are highly contaminated by foreground radiation, which is very important just because such foreground radiation is much, much stronger than the actual signal. And then we are trying to learn something from them. And as a result, here what I'm showing is one particular astrophysical parameter that we used. And on x-axis, it's predicted value. On y-axis, it's true offset of true value given the predicted value. And the different lines are different like slightly different architectures that we used. And with such kind of more optimal encoding of our information, we were able to get 8 times better results for our flagship model with respect to some previous results given in gray. And this was taking into account that previous analysis used global signal and had much higher resolution. But very importantly, once we recover such a plot, here we don't know what is the error of the neural network. That's the first thing. And the second thing is that such plot doesn't represent the actual posterior of our parameters, and that's what we are interested in. And so this is the step that we are going further. But before that, I just wanna say that in this analysis, once we have this network trained, yes. So in this work that we've done, this is just the parameters that we started with. So it's a regression. Yeah, it's a regression to the actual parameters. Yeah. Okay. And once we train this in exactly such a way, in a regression way, then we can actually infer what our network sees. So what I'm showing here is the actual simulation, and then here is what the network gets at its input. And what we can do, we can calculate the Jacobian of the output parameters given the input image. And if we do that, basically what that means is that we are saying, okay, how much does this particular parameter changes if I knob a bit the value in particular pixel, right? And from such image, then we can try to see where the network looks for the value of a particular parameter. And I haven't had time to explain the actual parameters, but for example, this zeta is controlling how efficient is the universe ionized, or how efficiently it is getting ionized. And this is particularly controlling this epoch of reionization. And so we can see that the network really focuses only on this part of our data set and not taking so much look in the rest. So this is like a sanity check that, I don't know, we didn't write 4 numbers of our parameter in the corner of the network, and that's it. Thank you. Okay. Okay. However, now I would like to go to our second part and to do the actual inference. And so what is generally done is that one just calculates a power spectrum, and then from this power spectrum writes some kind of likelihood function. But we would like to go further. And as I mentioned, analytically, this likelihood function we cannot find out, and also numerically it would be possible to trace it somehow, but it's just not feasible to compute something like that. And so, as I mentioned, 2 choices, as we saw even today, is that you take a power spectrum and you calculate likelihood as a Gaussian, with diagonal covariance matrix or with the full covariance matrix. However, we would like to go to higher order terms, and for something like that, we have to go into likelihood-free inference. So we have to somehow get to that terms or bypass them in some way. So the first analysis that we did was just to take a look, is there any benefit, for example, if we take just full covariance matrix with respect to diagonal covariance matrix, is it worth it or not? And so this is maybe not relevant in general, but it's relevant for 21 centimeter community because no one was actually checking that. And basically, we found out that just by taking covariance matrix, we get order of magnitude more information, and this translates into 26% average better constraint for each sigma, which is really a lot of information that we are throwing away if not taking the covariance matrix. But let's then try to go further. And to go further, we have to use likelihood-free inference. So the likelihood-free inference is a method in somehow, as I said, bypass or do something with the likelihood function and not explicitly writing it. And two common methods is approximate Bayesian computation, which bypass the likelihood completely, or we can fit the likelihood function with, for example, density estimation, with some density estimation technique. The way that this works is you can imagine, for example, that you have here one of your parameters, and here on y-axis you have one summary, right? And what you do, you take your parameter, you calculate your simulator, you compress it, and you get your summary. And then you plot the dots here in this space. And basically, those are dots which represent a probability function of theta and summary. And then in this space, the likelihood function lays if we condition this function to theta. And so basically, then what we do, we can fit this function with the sum method, or other choices. So we can fit the full distribution, or we can fit conditional distributions. So to get posterior directly or likelihood function. So any of the methods have its benefits, and we can do any of those. For the actual density estimation, we are using normalizing flows. They are neural representation of a probability density function. They work in a way that you start with the Gaussian noise, and then you do incremental changes in your probability density function to get what you want at the end. And if all of those transformations are invertible, then by knowing your starting distribution, you can then get your final distribution very easily. And yeah, so neural normalizing flows are just then training the weights of the network to do this procedure. Thank you. Finally, as a final result, we can then recover the posterior of our parameters. So here I have 5 astrophysical parameters, and we can get the actual posterior for some particular mock observation. And the benefit of this is that we have all of higher moments in a distribution, and also what is generally done is that when you write analytical likelihood, then you fix covariance matrix, for example, across your parameter space. This covariance matrix and also all higher moment terms are varying then across the parameter spaces. So those are the 2 main benefits of this. And generally, we are then getting much more constraints than using a purely Gaussian likelihood function. But the important caveats are because we are using neural density estimator, did the training converge? Is this posterior that we are getting overconfident, underconfident? Is it biased? And so we have to check this somehow and perform some consistency checks. And for this, we are using simulation-based calibration, which is based on observation that the prior that we are starting with is equal to the data averaged posterior. So what that means is, maybe if I can write just on the blackboard. So what that means is that you have your prior function and you sample from it. Then you simulate your data. So you have your simulator taking your parameters, and then you have your likelihood function, right? Likelihood function given this particular y and this particular theta, and for that you recover your posterior given that particular data, this particular data. And then if you do this bunch of times, you can just average this function that you get, and this should return you to the prior. And this is what this integral is showing. And basically, this SBC is then casting such kind of integral into 1D rank statistic distribution, which is showing you, are your posteriors overconfident, underconfident, or biased by the shape of it, like if it's concave, convex, or shifted in one direction. And that's exactly what we did. So for all of our parameters, we calculated this SBC. And here's just expected error of it, and we can see that it roughly goes into 2 sigma that we would expect. However, we have some overshootings, which shows that we have a bit of overconfidence in our posterior. However, this is a check that we are doing more or less fine. And there are some methods in which we could improve that, but I think I'm out of time, so I will not go into that. The problem is that it's quite expensive to compute, and one has to have very good method of sampling the posterior to be able to get such an analysis. And I will leave you with conclusions and maybe take a question or two.
Thank you for the interesting talk. I'm sorry I didn't quite follow how the simulation-based calibration by checking the prior can get you if the posterior is well estimated. Maybe I misunderstood.
Could you repeat the question?
Yeah. In the simulation-based calibration, you are calibrating your prior or your posterior? I didn't understand exactly what you do. Because the question was how well estimated was the posterior.
Exactly. So you recover this posterior, which is based on some neural network, underlying neural network, and then you want to check if it is a good posterior, if it is overconfident, underconfident, or so on. I mean, this SBC is like a general framework to testing your Bayesian inference pipeline. So if anything went wrong in your Bayesian inference pipeline in any step, then this will show you something, right? So it is applicable also in our case of this density estimation, but it could also be used, for example, in saying, okay, I'm taking Gaussian likelihood, how wrong I am with this Gaussian likelihood, right? So in recovering of my posteriors.
But you check with the prior. That's what you're doing, no? You are checking with the prior how wrong was the likelihood.
Exactly. So what I said is that, like, if you average your posteriors bunch of the times, then this average should be your prior. Yeah, and basically prior is the only thing that you really know, right? So everything else could go wrong, but prior you know. So that's why this is, yeah.
Okay, thank you very much for the clarification.
More questions?
I wasn't completely clear on what the task or density estimation task was for the part 2. Can you elaborate a bit more? I mean, did you generate, what simulations did you generate, or what were the samples that it was trained on?
So, okay, I guess I can return on this plot. Yeah, so let's say here, so basically what I did then in my case, I have my astrophysical parameters. I'm sampling them out of my prior. I am making the actual simulations, compressing them, and then I get these summaries. And then I have just a list of the points of the actual parameters and the summaries. And then on this vector, I am fitting the distribution.
Is it a conditional density estimation, I guess?
Yes,
Yeah.
yes, yeah.
You learned the likelihood of the summaries conditioned on the astrophysical parameters.
Yeah, so like basically you can do any of these three things. So we are doing both conditioning. So let's say taking some mock simulation, compressing it, and then conditioning posterior on that mock. This would be learning this function, so theta conditional to the summaries, or you can learn the actual likelihood function, so summaries conditional to the parameters. Yeah, so you can do any of those.
And were these summaries learned the output of part 1, or are these the physical, the previously sort of?
So here, this particular result is. I did the analysis just for the power spectrum, but yeah, so this is work in progress of applying this to like some other set of summaries. Yeah, whatever you can think of. Yeah.
Okay, thanks.
Yeah.
More questions? No? Okay, let's thank the speaker again.
Thank you.